So today I am going to discuss with you this new term, that is partial molar properties or partial molar quantities in thermodynamics. So if we talk about some thermodynamic properties such as entropy, enthalpy, internal energy. So all these properties, they are extensive in nature. Extensive in nature means these properties of the system, they depend on the amount of the substance present in the system. Correct? So if you are varying the mass of the system, definitely their values will change. As far as intensive properties of the system are concerned, so intensive properties are those properties which do not depend upon the amount of the substance, whereas these properties depend only on the nature of the substance that is present in our system. So surface tension, viscosity, all these are examples of intensive properties. Whereas this entropy, enthalpy, internal energy, you know it very well, their values depend on the amount of mass present in the system. That means these are the examples of extensive properties. So we can face two type of systems in thermodynamics. One is open system, another one is closed system. So if we think about a closed system, then for a closed system, there is no change in mass of the system, means amount of the substance remains almost same. But suppose we are having an open system. So for an open system, the amount of the component that are present in our system may also get changed. So it means that the properties of the system, now definitely these properties have to depend on the amount of the substance, or you can say that the extensive properties will now be a function of number of the moles of various components of the system. So initially we were thinking that it is only temperature, pressure, volume, only these three parameters, they are controlling the states of a particular thermodynamic system. But this is not true. In case we are dealing with an open system, then the concept of partial molar properties or partial molar quantities came into picture. So partial molar properties or partial molar quantities, these are useful while explaining the behavior of an open system. And in addition to temperature, pressure and volume, we have to take into account the amount of the substance that are present in our system. Clear? Now we have to drive an expression of partial molar quantity. So in order to drive an expression for partial molar quantity, so suppose you are having a system and temperature of the system is T and pressure of the system is P, and your system consists of N1, N2, N3, N4, N5 up to Nj. Number of moles of component 1, 2, 3, 4, 5 up to J. So J components are there in your system. And temperature of the system is T, pressure of the system is P. So accordingly, what will happen? We have to define this property X, any property of the system X. This must be a function of temperature as well as pressure. But in addition to temperature, pressure, we have to take into account the number of moles of various components of the system. Means if any of the property of the system is described, then for that type of property, we have to describe a function. Suppose we are defining a function x. So capital X function is defined. It is a function of temperature, pressure, N1, N2, N3 up to Nj. Means we have taken into account temperature, pressure as well as number of components or number of moles of various components present in our system. Where temperature, pressure, this is very simple thing for you, but N1, N2, N3, N4, N5, Nj, these are nothing but these are the number of moles of component 1, component 2, component 3, like component J. So equation number 45 is very clear to anyone. Correct? Now N1, N2, N3, there some we are defining again by capital N. So the total number of moles present in this system will be equal to N1 plus N2 plus N3 up to Nj, and we are defining a new number that is capital N. So this property X, when this property will undergo a change, then this change may be due to change in temperature, due to change in pressure, due to change in number of moles of one component, due to change in number of moles of second component, due to change in number of moles of third component. So like that, this property may undergo various type of changes. So the change in the property X, that we would like to denote by dx. So dx is the small change in the property x that we have defined. So the change in the property dx when temperature, pressure as well as the number of moles are changing, then this dx will be defined as del x by del t, यानी कि rate of change of x with respect to temperature, keeping pressure as well as total number of moles constant, and small change in temperature dt. So first term is del x by del t at constant pressure, constant capital N into dt. And similarly, another term will be due to pressure change. So the term due to pressure change will be equal to del x by del p at constant temperature as well as constant total number of moles times dp. Similarly, the third term will be due to change in number of moles of component 1. So it will be del x by del n1, and now we have to keep temperature, pressure as well as other components as constant n2, n3, n4, n5, ng. And it is to be multiplied by dn1. dn1 is a small number of change in component 1. Similarly, the next term will be del x by del n2, the contribution due to change in number of moles of second component, and we are keeping temperature, pressure, n1 and n3 up to nj as constant, and then this is dn2. Similarly, for ith component, we are defining this contribution as del x by del n I, temperature, pressure, comma n1, n2 up to nj. All these are to be taken as constant, and this is to be multiplied by small change in the value of this ith component, that is ni. Similarly, for last component present in our system, we are having a term that is del x by del nj, temperature, pressure, n1, n2, n3, ni, and up to nj minus 1. So it is wrong here. So last term should be equal to nj minus 1, and then this is dnj. So we have so many terms in this expression. For each parameter, we are having a term due to change in temperature, another term due to change in pressure, another term due to change in number of moles of first component, another term due to change in number of moles of second component. Like that, this we are having the last term due to change in number of moles of jth component. Clear? And if del x by del t is concerned, so it is the rate of change of x with respect to temperature when a small change in temperature is carried out, suppose dt, and keeping all other parameters as constant. We have taken pressure as well as n1, n2, n3 like that as constant. Now this quantity, what is that quantity? Quantity that is del x by del ni, यानी कि rate of change of x, rate of change of your property of the system x with respect to the change in number of moles of ith component, means del x by del ni. This rate of change of x with respect to ith component, keeping temperature, pressure, n1, n2 up to nj as constant, this term is known as partial molar property of ith component. Is it clear? So we have defined partial molar property due to ith component. If you are defining it for jth component, then what will be the value? This value will be equal to del x divided by del ng. Del x divided by del ng, temperature, pressure, n1, n2 up to nj minus 1, all these terms will be constant. So this expression, that is del x by del ni, keeping all other parameters are constant. So this expression is represented by this new term, that is capital X bar for ith component. So this capital X bar for ith component, this is known as partial molar quantity or partial molar property of ith component. Students, any problem till now?
No, sir.
No, sir.
So this partial molar property, you can define it as a thermodynamic quantity which shows what this expression is showing. This expression is showing that an extensive property of a solution or a mixture. Because why we are talking about mixture? Because we are having a number of components. So an extensive property of a solution or a mixture, it changes with the change in the molar composition of the solution while keeping the temperature and pressure as constant. So it is a partial derivative of that extensive property with respect to the amount of the component of our interest in which we are interested. So many type of components we may be interested. So this partial molar property is to be defined in terms of the component of our interest. So each and every extensive property of a mixture, it has its corresponding partial molar properties. So for any component ith, suppose we are having a component I. So partial molar gives free energy. Suppose we are talking about gives free energy of the system. Then this X, this general property or general extensive property will be gives free energy. So if we define partial molar gives free energy, then partial molar gives free energy for ith component will be what? Rate of change of gives free energy with respect to ith component, means del G by del Ni. And what we have to do? We have to keep temperature, pressure, N1, N2, N3 like that up to Nj constant, except Ni, because Ni is varying, correct? And then it is to be multiplied by dni. So this is what? This is what? Your gi bar. And partial molar internal energy, if you are defining partial molar internal energy, then it will be the rate of change of internal energy with ith component, that is del ni. So del u by del ni, temperature, pressure, n1, n2, n3, all these things are to be taken as constant except what? Ith component. This will be represented by u bar I. Similarly, we can define partial molar enthalpy. If we are interested in enthalpy of this system, that is an extensive property. So this partial molar enthalpy of the system will be defined as del H divided by del Ni, and temperature, pressure, N1, N2, N3 like that. All these things are to be taken as constant except your ith component. So Ni will not be there in this expression, and this term will be represented as H bar I. So now we have defined partial molar property for a particular or ith component. We have defined partial molar gives free energy. What is the expression for partial molar gives free energy? What is the expression for partial molar internal energy? And what is the expression for partial molar enthalpy of a particular system? Now, let us talk about physical significance of this partial molar quantity. What is the physical significance of this partial molar quantity? So the quantity xi, that is partial molar quantity of ith of a particular extensive property x, it represents the actual value of x per mole of the ith component of the system. So it represents the actual value of x per mole of the ith component of the system, and sometimes this value may be same or different from the actual molar value x star in the true state. So sometimes in true state and in that state, both these type of things may be same, but Most of the time these two parameters are not same, because whenever a number of components are there and due to change in their molar concentrations, this parameter have to undergo a change in its value. So these two values, one value we are having partial molar value and another is having actual molar value. These are same in case of ideal systems only, but most of the time we have to face non-ideal systems. So for non-ideal systems, these two values, these are different because of the interactions between the constant particles, atoms, and molecules that are taking place. Or you can say that the actual molar value, it has to gets modified to partial molar values. So this partial molar value may not be same throughout the whole of the solution, since the extent of interaction may vary according to the amount of constituents. So amount of constant means if you are varying their amounts, then definitely its value has to change. So that is the significance of partial molar quantity. Means if you are changing, you are varying the amount of a particular component, its value has to change. But if you are talking about the actual molar value of a particular quantity, then it will not change because its value is defined for per mole. So partial molar quantities, these have to depend on amount of substance, whereas the actual molar value, it does not have to depend on, because it is defined only already for. So we have defined these two things. What is partial molar volume? So partial molar volume of a substance, suppose we are interested in the ith component of the substance. So partial molar volume of a substance in a mixture, it is nothing but it is the change in the volume per mole of the substance I that you are adding to a large volume of the mixture. What does it mean? You are having a large volume of the mixture. So many substances are present there. One, two, three, like that up to J. J substances are there. Out of these J substances, we are interested only in the ith component, ith substance. So for ith substance, if you are defining the partial molar volume, then this partial molar volume will be nothing but it will be the change in the volume that will takes place per mole of the substance I addition to the large volume of mixture. So this is the meaning of partial molar volume. So in the case of ideal solution, the partial molar volume of ith component will be equal to its molar volume, because in case of ideal substance, no special type of interactions has to take place. But in case of non-ideal solution, this partial molar volume will be definitely differ from that of your ideal volume. So this determination of partial molar volume for two component systems, please go through that one. So you can calculate its value. Now I am going to this another important parameter, that is partial molar Gibbs free energy. That is quite important thing. So partial molar Gibbs free energy, this is also a partial molar property of the system, and we are talking about Gibbs free energy. So we have already defined partial molar Gibbs free energy. This is what rate of change of Gibbs free energy with respect to change in number of component, ith component. So del G by del Ni, temperature, pressure, N1, N2 up to Nj, all these things are to be taken as constant, but Ni we are changing. So this partial molar Gibbs free energy is denoted by G bar, and in subscript we are having this ith component, and sometimes you may also write it as ui, correct? So ui is partial molar Gibbs free energy, it is gi bar. So this partial molar free energy gi or pm is simply we are writing it for partial molar quantity. So this is the most important partial molar quantity, and this is also known as chemical potential, and we denote chemical potential as mu, correct? So mu or G I bar, this is nothing but it is the rate of change of G, means how the Gibbs free energy changes when you are doing some changes in the number of moles of ith component. So this chemical potential is the change in the free energy of the system, means how much free energy of the system will change, which results on addition of 1 mole of a particular component or particular substance to a very large system, such that the overall composition of the system does not change while keeping the temperature and pressure as constant. So this is the definition of this chemical potential. This is nothing but it is the change in free energy that takes place when you are adding 1 mole of that particular substance to our system, and our system should be in such a way that overall composition of the system should not change while keeping the temperature and pressure as constant, because we have to define all these partial molar quantities keeping all these parameters as constant. So temperature, pressure are to be taken as constant, and 1 mole of that particular substance we have to add to our system. How much amount of Gibbs free energy change takes place, that has to decide what is the partial molar Gibbs free energy and what is the value of this chemical potential. So now chemical potential is clear to all of you.
Yes, sir.
So simply you have to add 1 mole of that particular substance whose chemical potential you want to measure, and keeping the concentration of all other components as constant. And in addition to that, what you have to ensure that the temperature of your system is constant, pressure of your system is also constant. Clear? Now let us see, if we write free energy change, so change in free energy, what we are doing, that expression x we are representing, or we are replacing this x by g. So change in Gibbs free energy g, that will be dg. So total change in Gibbs free energy will consist of a number of terms. The very first term is rate of change of g with respect to temperature, pressure and total concentration of your system is kept as constant, then it is dt. So the first term is the contribution due to change in temperature. Now change your pressure. So pressure change term will be equal to del G by del P. Temperature and total number of components, these are constant. And then dP. dP is the small change in pressure that you are carrying out. Plus third term will be equal to del G by del N1, pressure, temperature, N1, N2, N3, like that. All these components are to be taken as constant, and then dN1. So we are representing it del G by del N1 as mu1. Correct? Is it mu1 or not? Del
Yes, sir.
del N1 at temperature, at constant temperature, pressure, N2, N3. If all these things are constant, then definitely it will be mu1, because mu I we have defined in equation number 67. So it will be mu1 times of dn1. dn1 is what? Small change in the value of this first component. Similarly, we are having mu2 times dn2. Similarly, mu3 times dn3, like that. It will continue up to mu j times of dng. So equation number 68 is clear to everyone. In 68, what
Yes, sir.
we are interested in the small change in the value of dg. So this small change in the value of dg will consist of a number of terms. First term is the contribution due to change in temperature. Second term is the contribution due to change in pressure. Third term is the contribution due to change in the number of moles of first component. Second term, then next term is due to change in number of moles of next term, then next term, and final is the contribution due to change in number of moles of the last component that you have defined as jth component. Is it clear?
Yes, sir.
mu1
Yes, sir.
mu1 mu2 mu3,
Yes, sir.
these are what? Chemical potential of your ith component, means first component, second component, gth component. So all these are the chemical potentials of your corresponding constituent, first, second, gth. Now suppose you are treating your system in such a way that your temperature and pressure remains constant. In that situation, if your temperature and pressure is constant, then what will happen? The change in this property dg at constant temperature and pressure. We are talking about equation number 69. So this change in Gibbs free energy at constant temperature and pressure will be equal to what? Simply you have to substitute dt equal to 0, dp equal to 0 in 68 equation. So you will jump to 69 equation. At constant temperature, dt will be 0. Similarly, at constant pressure, dp will be 0. So the first term in equation number 68 and the second term in equation number 68, it will vanish because dt is 0, dp is 0. So this dg at constant temperature and pressure will be equal to mu1 times dn1 plus mu2 times dn2 plus like that mu j times of dng. Equation number 69 is clear. Now, so let this system has definite composition means N1, N2, Nj number of moles of first, second, third up to jth component. These are respectively uh, some definite values. Then if we integrate this equation 69, so on integration, we will be having on left hand side, this differentiation will be cancelled out by integration. So we will be having this property gives free energy G of the system at constant temperature, constant pressure, and constant number of moles of all the components because total N is constant. So on integration, this will be mu, this will be mu1, second will be mu2 and 2, third component will be mu3 and 3, like this it will be mu j and j, or g will be equal to n1 mu1 plus n2 mu2 plus nj. So this we have obtained with the help of integration. So on integration, equation number 69, we are having this equation number 70. So if we think about this equation, then from this equation, the chemical potential, we can define it as the contribution to the total free energy. Total free energy G hai. So for uh, total free energy, what is the contribution to the total free energy of a system by 1 mole of each component in the mixture while keeping the temperature, pressure as constant? And Gibbs free energy of the system, this is the sum of the n mu terms for individual constituents of the system. So like this, we have defined partial molar quantities, partial molar properties, and we have derived an expression for this Gibbs free energy G. It is nothing but sum of the chemical potentials of all the components, and these chemical potentials have been multiplied by their respective number of moles that are present in our system. So with this, I would like to stop recording.